Hello class, this is continuation of our lecture in fluid flow measurement. We are now on weirs. So weirs are overflow structures which are built across an open channel for the purpose of measuring or controlling the flow of liquids. Weirs may be rectangular, triangular, trapezoidal, circular, parabolic, or any other regular shape. But most commonly, the used shapes for weirs are rectangular, triangular, and trapezoidal shapes. Now, we go directly on the formula being used in measuring the flow rate within a weir. For rectangular weir, we have a general formula of Q, which is equals to 2/3 C, the square root of 2G times L, then the quantity of the sum of H plus HV raised to 3 over 2 minus H of V raised to 3 over 2. So C is your coefficient of discharge. H, that's the height of the liquid. Okay. H of V is your velocity head of approach. Okay. Of approach. Or it is a common practice to combine 2/3 C, the square root of 2G, this terms right here, into a single coefficient, which is CW, or the coefficient of Weir, or the Weir factor, to shorten the equation. So here is your general formula for a rectangular Weir. Okay. Next. Now, if we are going to neglect the velocity head of approach, so it means that if we are going to ignore the velocity head of approach, h of v, so this will be 0, what will remain is this equation. We have q, or the discharge, equals to 2/3 c, the square root of 2gl h raised to 3/2. Again, the L, that's the length of your weir, or if you are looking at the cross section of the weir, that's your width. And H is the height from the liquid surface to the bottom end, or of the opening of the weir. Okay. Or again, if we combine these terms, we have the coefficient, or the weir factor, CW, multiplied by LH raised to 3/2. Now, using Francis formula, the coefficient, or the weir factor, is equivalent to 1.84 for SI units. But if we are in English system, that weir factor is equivalent to 3.33. Okay, it's for English. So from our general formula, we have now the solution using the Francis formula of 1.84 L multiplied by quantity of H plus HV raised to 3/2 minus H of V raised to 3/2. Or, neglecting the velocity head of approach, we can have this equation right here for the flow rate. Q equals to 1.84 LH raised to 3/2. For triangular weir, here's our formula. Q is equals to 8 over 15 C, the square root of 2G, tan theta over 2 H raised to 5/2. So H is the height from the liquid surface to the bottom, or the vertex of this triangular weir, and we have an angle theta, or that's the weir angle. Okay, theta. For a standard 90 degrees weir, we have formula Q equals to 1.4 H raised to 5 halves, or you just substitute. Okay, 90 degrees here. Okay, next, Sipuliti weir. Sipuliti weirs are trapezoidal weirs with side slope of 1 horizontal to 4 vertical. So here's a Sipuliti weir. It is trapezoidal in cross section. We have a formula of Q equals to 1.859 LH raised to 3 half. This is for SI units. Okay, so for unsteady flow weir with variable head, so it means that if we have a weir here, then as the liquid or the fluid flows on this opening or in this weir, for unsteady or variable head, it means that uh, the head of the liquid changes with respect to time as it flows on this opening on the weir. So in order for us to compute the time required for each to reach a certain level from its initial level or initial head, h1 and h2, so we have this formula of time equals to 2as area of, or the surface area. Let's say if this is rectangular in shape, this surface area right here. Okay, that's your A sub S. Then weir factor CW times L, or the crest length of the weir. It's L. Okay, this is the length. Multiplied by 1 over the square root of H2, which is the final head, and subtracted by 1 over the square root of H1. H1 is your initial head. Okay, so let's now start solving some problems. Okay, problem number 1. During a test on a 2.4 meter suppressed weir 900 mm high, the head was maintained constant at 300 mm. In 38 seconds, 28,820 liters of water were collected. What is the weir factor CW? So we have a 2.4 meter suppressed weir. So 2.4 meter here is your length. Okay. Sample number 1. During a test on a 2.4 meter suppressed weir 900 mm high, the head was maintained constant at 300 mm. In 38 seconds, the amount of water collected is 28,820 liters. What is the weir factor CW? So based on the given, we have here a 2.4 meter suppressed weir. So what 2.4 meter is your length. That's your length. And we have a height of 900 mm. So 900 mm is pertaining to the weir. So the weir, okay, if this is your channel, this is the total height of the channel. If we are going to put the weir here, means that we have a 900 mm height from the bottom of the channel. Okay, 900 m. So as a whole, this is your open channel, but in order for us to measure the discharge, okay, we put a suppressed weir. Okay, this portion right here is your weir. So from the overflowing liquid above the weir, we can now measure the the amount of liquid that is passing through this section. Okay, so we had 900 mm or 0.9 meters height of the weir. Then the head was maintained constant at 300 mm. So it means that our head now should be measured from this point, okay, up to this point. Let's say here is your water level. So the head is maintained constant at 300, okay, so that's 300 mm. So let's make it realistic, okay. Say this is your weir, okay, and we have a height of 900 mm and a constant head of 300 mm, okay. That means this is just the opening of the channel where the water is flowing, okay. It is being suppressed by this weir right here. So let's solve now the required here, which is the weir factor. It is given here that we have a time of 38 seconds. It collected a volume of 28,820 liters. So if we convert that to cubic meters, that's divided by 1,000, that's 28.820 cubic meters. Discharge is equals to volume with respect to time. So therefore, 28.820 divided by time, which is 38 seconds, is equals to the discharge 28.820 divided by 38, 0.75842. Okay. 75842 cubic meters per second. That's your discharge. Then since we have a discharge, we can determine the velocity of approach. Okay, the velocity is discharge over cross-sectional area. Okay, so velocity of approach. Discharge 0.75842 cubic meters per second divided by the cross-sectional area. Okay, so this cross-sectional area is just the opening. Okay, opening in the channel, which is 2.4. That's the width, and the height of total of 1.2. Okay, so for the velocity of approach, the area that we are going to use here should be the total area of the whole channel, okay, the area of the whole channel. So that's the velocity of approach, means that's the velocity, okay, that's the velocity before it approach the weir itself, okay, means before it approach the weir, that's your velocity. But when it passes through this opening, because we have a suppressed weir, that velocity will increase. So what we need here is the velocity of approach. So that's why we use the area of 2.4 by 1.2 meters. This is total of 1.2 meters. That's the total height. Okay, so the velocity of approach is equals to 0.75842 divided by 0.75842 divided by 2.4 times 1.2. The answer is 0.26334 meter per second. Then we can now determine the velocity head h of v using this velocity approach. V squared over 2g. Substitute now 0.26334 meter per second raised to 2 divided by 2 times 9.81 meter per second squared. So h of v is equals to 0.26334 over 2 times 9.81, 0.0134 meters. That's your velocity head for this problem. Then we can now use the general formula for a rectangular weir, which is Q equals to CW L, quantity of H, plus H of V raised to 3 halves minus H of V raised to 3 halves. So we already determined the discharge 0.75842 cubic meters per second equals to the unknown Weir factor. L is 2.4 meters, then multiplied by H. Okay, the H here is the head, okay, the head of the opening of the channel. That's 300 mm or 0.3 plus the head velocity head 0.0134 raised to 3 halves minus 0.0134 raised to 3 halves. Okay, the only unknown is CW. I will directly solve that. 0.75842 is equals to unknown CW times 2.4 times the quantity of 0.3 plus 0.0134 raised to is to 3 halves. Okay, 0.3 plus 0.0134 raised to 3 halves, that's 1.5 minus 0.0134 raised to 3 halves, or 1.5. Okay, close parenthesis. That's equals to, okay, plus shift solve. Okay, the value of x, or the unknown variable CW, is 1.817. Okay, that's unitless because that's a Weir factor. That's the answer for this particular problem. Next, another problem. A rectangular sharp crested weir 15 meters long with end contractions pressed is 1.5 meters high. Determine the discharge when the head is 300 mm. Okay, so they said here that we will use Francis formula. Francis formula is Q is equals to our Weir factor is 1.84, then we multiply L, H raised to 3 halves. Okay, so substitute now the given 1.84. Our L is the length, which is 15 meters. And how about the H? The H should be the head. Is it 1.5 meters or 300 mm? So the head for this solution should be 300 mm or 0.3 meters because our suppressed weir. Okay, if this is your open channel, we have a length of 15 meters and a total height of 1.5. Okay, so it is said here that uh, we will have a head, okay, at 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 the discharge of 300 mm. Okay, so we will have a constant head of 300 mm in order for us to determine the discharge. So it means that the opening, when we use weir, where the water is flowing, has a head of 0.3 meters. Okay, so let's now solve using Francis formula. 1.84 times 15 and 0.3 raised to 3 halves. That's raised to 3 halves or raised to 1.5. 1.5. Okay, the answer is 4.535 cubic meters per second. Okay, okay, so that's the answer for this problem. So the Weir factor 1.84, actually it has an equivalent unit. That's why we ended up unit for the discharge of cubic meter per second. So the unit here is in meter, it is raised to 3 halves. So as you recall earlier, Weir factor is a combination of 2/3 C square root of 2G. So this unit of time came from the square root of 2G unit. Okay, next problem. A sharp-crested contracted triangular weir with a weir angle of 80 degrees carries water under a head of 0.955 meters. Find the flow of water over the weir. Let the coefficient of discharge be 0.6. So the formula for the discharge in a V-notch or triangular weir is equals to 8 over 15 c the square root of 2g tangent theta 2 multiplied by h raised to 5 halves. Now we simply substitute all the given here. 8 over 15 c is 0.6 square root of 2 times 9.81 second squared, tangent of the angle, weir angle 80 degrees divided by 2 multiplied by h, head 0.955 meters raised to 5 halves. So the Q is equals to 80 over 2 is 40 multiplied by 0.955 raised to 5 halves. 5 halves is 2.5. So the answer is 1.06038 or 1.06 cubic meters per second. Okay, that's the answer. Next problem. The discharge over a stipulated weir is 1.315 cubic meters per second. The crest length is 2 meters. Find the head. Okay, so the formula for a stipulated weir, which is a trapezoidal weir, is 1.859 LH raised to 3 halves. Now substitute all the given. 1.315 cubic meter per second goes to 1.859. Length 2 meters. H is unknown, raised to 3 halves. So let's directly solve this in a calculator. The H is equals to 1.859 times 2 times x raised to 3 halves, okay, or 1.5. So the answer is 0.5 meters. That's the head of your trapezoidal weir or Cipollite weir. Okay, last problem. A rectangular suppressed weir of length 1 meter constructed or cut at the top of a tall rectangular tank having a horizontal section of 20 meters by 20 meters. Okay, that's your dimension, 20 by 20. If the initial head over the weir is 1 meters, 1 meter, compute the time required to discharge 72 cubic meters of water. Okay, so I think initially this is 1 meter. Okay, the opening or the head is 1 meter above the bottom of this opening. Let's say here is your liquid that's having a 1 meter head. So of course we have a general formula in determining the time for this kind of question, which is 2 area of surface area over CWL, quantity of 1 over square root of H2 minus 1 over the square root of H1. Okay, so based on the given, we already have the surface area, that's 20 meter by 20 meter, or that's 400 square meter. CW said here to use Francis formula, that's 1.84. Another crest length, okay, that's constant, 1 meter. This is your crest length, 1 meter, or the width of the opening. And okay, how about H2 and H1? H2 and H1. So for H1, that's your initial head, that's 1 meter. But the problem is H2. How can we determine H2? For H2, all we need to do is to determine the drop of water level after it discharges about 72 cubic meters of water. So the new water level now, of course, is lower than the initial head of 1 meter. So how can we compute that? So since it dropped, the water level dropped from its initial head of 1 meter, so the reduced volume, which is 72 cubic meters, is also in the shape of rectangular prism. Okay. So in order for us to compute that volume that is spilled in this container, okay, we will use the volume 72 cubic meters. So in order for us to determine that drop, okay, we'll just find the volume of this rectangular prism, and this is said to be this imaginary volume, or the volume that is discharged, okay, or spilled after 72 cubic meters. So to compute the volume, we have a surface area of 20 by 20 and just multiply the drop, okay, drop level. So 72 cubic meters divided by 20 by 20, that's your drop. So the drop is 0. When we compute this, 72 over 20 by 20, 0.18 meters. That's your level drop. So from initial level 1 meter, let's just subtract the drop of 0.18. H2 now is 0.82 meters. Okay, now let's substitute all that values here from T. T is equals to 2 times surface area 400 over CW 1.84. L is 1 crest length, and we have 1 over the square root of H2 0.82 minus 1 over the square root of 1 for H1. So the time is 2 times 400, 1.84 times 1. Okay, here's your answer. 45.354 seconds. Okay, that's the time required in order for it to discharge 72 cubic meters of water. Okay, that ends our lecture for Weirs.